Good afternoon, everyone. Our topic today is LOX, liquid oxygen, specifically how it's produced at industrial scale through cryogenic air separation. This presentation covers the whole process chain, from pulling an ambient air off the atmosphere all the way to delivering a cryogenic fluid pure enough to run a rocket engine. We'll hit the thermodynamics, the separation science, the energy trade-offs, and the safety hazards, tying it directly back to what we've covered this semester in separation processes. Let's get into it. So what exactly is LOX or LOX, and why does it matter? Liquid oxygen is simply O2 that has been cooled below its boiling point of negative 182.96 degrees Celsius or 90.19 degrees Kelvin. At that point, it transitions from a gas to a pale blue liquid with a density of 1,141 kilograms per cubic meter, roughly 800 times denser than gaseous oxygen at standard conditions. That density difference is precisely why you'd want it in liquid form. Energy and mass density matter enormously when you're storing propellant on a rocket. Looking at the critical properties, the critical temperature is 154.6 degrees Kelvin, and the critical pressure is 50.2 barometers. What that means practically is that above 154 degrees Kelvin, you cannot liquefy oxygen no matter how much pressure you apply. This sets a hard thermodynamic floor on your process. You must cool below that temperature before liquefaction is possible. Industrial purity targets are greater than or equal to 100 or 99.5 mole percent O2, a bar set purely by propulsion applications where trace contaminants can be catastrophic. Now, why does LOX matter at scale? The slide breaks it down into three buckets. First, rocket propulsion. LOX is the oxidizers of choice for virtually every modern high-performance launch vehicle. The Falcon 9 uses LOX/RP-1 in its Merlin engines. The Space Launch System uses LOX/LH2 in its RS-25 engines. Vulcan Centaur, New Glenn, Starship, all LOX-based. It's the industry standard because oxygen has a high specific impulse contribution and is relatively stable or safe compared to alternatives like nitrogen tetroxide or RFNA. Second, medical and industrial use. Hospitals use LOX for life support and respiratory therapy. Steel manufacturers use it in basic oxygen furnaces, literally blasting pure oxygen to molten iron to oxidize carbon. Welding, water treatments, chemical synthesis, the demand is broad and constant. Third, and this one is particularly relevant given where airspace is heading, in situ resource utilization, or ISRU. NASA's MOXIE experiment aboard the Perseverance rover demonstrated electrolytic oxygen production directly from Mars' CO2 atmosphere. That's a proof of concept for producing LOX on Mars for propellant depots that would support a crewed return mission. The same cryogenic separation principles we're discussing today would apply, just in a radically different environment. Commercially, the global LOX market is estimated around $6.1 billion as of 2024. Key consumers include SpaceX, NASA, ULA, and industrial gas companies like Linde and Air Products, who operate large-scale air separation plants. With that context set, I'll hand it over to Josh, who will walk through the overall process flow and the first major separation step.
Yeah, so now that we know a little bit about liquid oxygen and what it's been used for, we're going to break down the process of cryogenic air separation to produce liquid oxygen step by step. So the first step we have on this process is going to be the air intake and filtration. This is essentially when atmospheric air is pulled in through the inlet filters to remove the initial particulates and the bulk amount of the moisture in the air before any compression occurs. Second is going to be the molecular sieve absorption. This is a critical pretreatment step when feed air is passed through the zeolite bed to strip out water vapor and carbon dioxide to sub ppm levels. I'll cover this in details in just a moment. The third step is going to be compression and cooling. This is when the clean dry air is compressed through multi-stage compressors with intercoolers to approach isothermal compression, and then which is pre-cooled against returning product streams. This is all kind of may sound very similar because, again, we've seen a lot of these things in class. The fourth step is liquefaction via the Linde cycle. This is when compressed air undergoes a Joule-Thomson expansion across the throttle valve, dropping temperatures down to approximately 90 degrees Kelvin, which is below oxygen's boiling point. and the liquid fraction is then produced through a flash drum. The final stage is going to be cryogenic distillation, where the liquid air mixture is fed into a double column distillation system, which is the main heart of this process, and it separates the oxygen, nitrogen, and argon to their target purities. So yeah, initially the feed into the system is going to be the atmospheric air. As we know, atmospheric air is roughly around like 78, 79% nitrogen with 21% oxygen and maybe 1% argon. Out of the other end, you want to essentially our goal is to get 99.5% liquid oxygen purity and liquid nitrogen at 99.99%, along with liquid argon at 99.9% purity. The entire process runs at a specific energy of roughly like 0.35 to zero point 0.4 kilowatt hours per kilogram of oxygen produced, making compression essentially the primary dominating cost in this whole process. Because of heat integration and turbine expanders, the primary ways to improve that are through that by implementing, which is exactly what chemical engineering is about. Yeah, so on to molecular sieve adsorption. We know a little bit about adsorption because we just covered it in class. But again, this is stage 2 of the process, and we're going to essentially use a temperature swing adsorption process. So after the initial pre-compression to around 4 to 8 bar, feed air enters the bed packed with zeolite, which is something they use commonly to adsorb onto, and activated alumina. These materials absorb the water vapor and CO2 through surface chemistry, and polar molecules like water bind really strongly to the lattice of zeolite. So why is this removal so critical? If we look at the table to this, like on the slide right here, water freezes at approximately 273 degrees Kelvin, which is well above our cryogenic operating temperatures of 90 degrees Kelvin. So if the water reaches that cold box, it's going to freeze solid and it's going to plug all of our heat exchangers. Carbon dioxide, on the other hand, freezes at 195 degree Kelvin, which will block the distillation trays even at very, very small concentrations in the parts per million. And these are both process-killing contamination events. The most safety-critical contaminant that could be in the air is acetylene, C2H2. This is a freeze point of 189 degrees Kelvin, and acetylene that makes it in distillation section can accumulate in the liquid oxygen. And what's worse about this is that acetylene is shock sensitive and it can detonate. This is a very critical hazard, and the reason hydrocarbon analyzers at parts per billion sensitivity levels are very mandatory in these plants and the bottom streams. The whole overall system uses a dual bed configuration. So bed A essentially absorbs contaminants online, and bed B is regenerated offline using hot nitrogen that's purging at approximately 200 degrees Celsius to essentially regenerate the bed by taking off the adsorbed species. The bed switched to every 4 to 8 hours, giving you a continuous feed flow without any interruption. And the outlet specifications are really tight. You want water below 1 part per million and CO2 below 1 part per million. So this is very fundamentally an adsorption process. Same time we've studied in class, we just have to meet a very, very tight purity requirement. And that just makes the engineering margin essentially zero. So now I'll hand it over to Damian to cover liquefaction and the distillation system.
Okay, so I'm Damian, and I'll be taking you through the thermodynamic parts of the process. And we'll start with the Linde-Hansen liquefaction cycle and then the cryogenic distillation system. So the Linde-Hansen cycle is how we get from cold, clean, compressed gas to actual liquid. It runs in 5 steps. So step 1, compression. Air is compressed to 150 to 200 bar through a multi-stage compressor with intercoolers. So we try to approximate isothermal compression to minimize work input. Step 2, recuperative heat exchange. The high pressure stream is pre-cooled in the counterflow heat exchanger against the cold, low pressure stream returning from the flash drum. So ideally, delta or change in temperature would approach 0. So the closer we get, the more efficient the cycle. Step 3, there's a Joule-Thomson expansion. So the cold high pressure stream passes through a throttle valve. So this is isenthalpic. So enthalpy is conserved. The initial enthalpy is equal to the enthalpy. And so there's a temperature drop governed by the Joule-Thomson coefficient, which is the partial derivative of temperature with respect to pressure at constant enthalpy. So for cooling to occur, the Joule-Thomson coefficient must be positive, meaning we need to be below the inversion temperature. So for oxygen, the inversion temperature is approximately 893 degrees Kelvin. So at ambient temperature, we're well in the cooling regime. The Joule-Thomson expansion drops our air mixture down toward 90 degrees Kelvin. So step four, phase separation. So the expanded two-phase mixture enters a flash drum. The liquid fraction is calculated from enthalpy balance. Um, Y underscore L equals to H underscore N minus H or minus enthalpy vaporization divided by enthalpy of liquid minus enthalpy of vapor. So the vapor and liquid fraction are separated here. So step five, vapor recycle. The unliquefied vapor returns through the heat exchanger, pre-cooling the incoming high pressure stream and closing the loop. So now we're going to go to the next slide six. Step three, cryogenic distillation slash double column system. So this brings us to the separation itself, cryogenic distillation in a double column Linde system. So the system consists of a high pressure column operating at 5 to 6 bar and a low pressure column operating at 1.3 bar. They're thermally linked by a condenser reboiler. So the HPC overhead nitrogen condenses against the LPC bonds oxygen, driving both columns simultaneously with a single heat integration unit. This is an elegant piece of process design. The pressure difference creates the temperature driving force for that shared heat exchanger. So the vapor-liquid equilibrium for a nitrogen-oxygen system is well behaved and nearly ideal. The relative volatility alpha is approximately 3.8 at 1 atmosphere, meaning nitrogen is nearly 4 times more volatile than oxygen. This is favorable for distillation. The equilibrium relationship is, Y star, whatever we learned in class. It's the standard relative volatility form, with alpha estimated as as the, as the ratio of pure component vapor pressures via the Antoine equation. For McCabe-Deely analysis in this class, it's a lot of words. So we work with binary systems using L over V ratios and operating lines. Here, the OPC typically runs at L over V of 0.6 to 0.7, and the minimum reflux ratio is determined by the Underwood method. Stage efficiency, mercury vapor phase efficiency, around 60% to 80% for tray clumps. To hit the required liquid oxygen purity of 99.5%, the LPC requires on the order of 60 to 100 theoretical stages. So modern plants are increasingly switching from sieve trays to structured packing, specifically products like Sulcer, Millipack Plus, which give HETP values of zero point 0.3 to zero point 0.5 meters and lower pressure drop per equilibrium stage. Lower delta P in LPC is directly tied to lower required compression energy in HPC. So with that, I'll hand it to Joseph for energy analysis, applications, and safety.
Thank you, Mr. Liamkeo. So the biggest energy user in LOX production is going to be the main air compressor. And this makes sense because the process starts by taking a huge volume of the atmospheric air, and then we're trying to compress it to a high pressure before we cool and liquefy it. And so this takes a lot of work. So the main air compressor takes about 72% of the total energy consumption. It's followed by 10% with the cold box losses, which is where heat is leaking into our cryogenic system. 9% to the nitrogen recycle compressor, which is where we use the nitrogen waste stream and it's compressed and cooled in order to sustain our cryogenic temperatures for liquefaction. And then 5% for pumps and auxiliaries, which is where we're just moving liquids or fluids. So these could be liquid oxygen or nitrogen. Another 4% for control and others. And so some ideas on how we could make this process more efficient would be to use turbine expanders. So utilizing turbo expanders, these expand the gas, but they also convert some of the energy, the pressure energy into shaft work, which the Joule-Thomson valves just waste. So a good analogy for this would be if you had a tire and then you let air out. Basically, what the turbo expanders are doing is they're utilizing the air that's leaking out to use like a small turbine in the flow, so some of that pressure energy is recovered. Another idea is heat integration, using cold outgoing streams to cool the warm incoming streams. So using cold nitrogen and oxygen outgoing streams to pre-cool the incoming compressed air. Also structured packing. One of the most common structured packings are Sulzer Millipack Plus. And basically these would help to reduce pressure drops and increase efficiency overall. and also variable speed drives. These let the compressors adjust speed based on demands because they don't always need to be operating at full capacity. And this reduces the partial load energy by around 8 to 12%. Another efficiency improvement that could be done is to utilize the waste nitrogen stream. So use the warm nitrogen waste, and it can regenerate the molecular seed beds by heating and purging out water and carbon dioxide. These are some applications for LOX production. So LOX production is very relevant to rockets and space systems. LOX itself is not the fuel, but it's an oxidizer, since combustion requires both fuel and oxygen. So when you're on Earth, the engines can just utilize the oxygen from air. But when you're in space, you can't do that. So rockets need to carry their own oxidizer. So here on the left, we have common LOX-based propellant combinations. So these are just some of the most common ones. The OF ratio is the oxidizer to fuel ratio, and that's just telling us how much oxygen is needed to compare to fuel. LSP is specific impulse, measures thrust generation per unit or propellant consumed, and that's measured in seconds. We can see, so the highest LSP value is the most efficient, and the LOX liquid hydrogen has the highest efficiency. But the thing with this combination is that hydrogen is very hard to store. And so the other different combinations like the LOX RP1, which is LOX and kerosene, that has a lower efficiency, but it's a lot easier to store than the hydrogen. So there are a lot of different considerations to take into account besides just the overall efficiency. Um, and on the right, we just get an idea for the LOX production scale, how much liquid oxygen is necessary for rockets, and how much is actually able to be produced. So at the bottom there, we see a large air separation unit's daily output is around 300 to 1,000 tons a day. But the Kennedy Space Center at its peak demand requires 3,000 tons a week. So um, yeah, the liquid oxygen is very important, and also in C2 resource utilization. So basically, they're trying to do experiments or do research to find out how we could not have to bring the oxidizers with us to space, but how we could generate them in space. So they did an experiment called the MOXIE experiment, where they were able to generate 6 grams per hour of oxygen utilizing Martian CO2 because Mars's atmosphere is mainly composed of carbon dioxide. But they still need to do work on looking into how they would further liquefy this oxygen for use. These are some of the safety hazards of LOX production. So oxygen enrichment, LOX doesn't burn, but it makes everything else burn faster and more violently. If LOX spills, it can evaporate and enrich the surrounding air with oxygen. Normal air is around 21% oxygen. So if that level were to rise above 25%, materials that normally would not ignite easily would start to become fire hazards. So in order to minimize this, you want to get rid of ignition sources. Another hazard is cryogenic burns. So LOX is around 183 degrees Celsius. Direct contact with it would cause tissue to get destroyed very quickly. Very similar to like a thermal burn. So some of the safety controls for this would be cryogenic gloves, face shield, non-absorbent clothing, and yeah. Another hazard is pressure buildup. When LOX warms up, it expands massively. Liquid to gas expansion ratio for LOX is around 860 to 1. So if LOX were to be trapped in a sealed container and warmed up, the pressure would rise rapidly. And if the pressure relief system were to fail, the vessel could explode. Another hazard is hydrocarbon contamination. Hydrocarbons like oil, grease, or propane are extremely dangerous in oxygen systems. In a cryogenic distillation column, contaminants can accumulate in the oxygen-rich liquid at the bottom. That would create an explosive mixture. Another hazard is embrittlement of materials. Many normal metals become brittle at very low temperatures. Carbon steel, for example, can become brittle below about negative 46 degrees Celsius. So at cryogenic temperatures, brittle materials could crack very suddenly. Another hazard is asphyxiation. Nitrogen can displace oxygen, and it's also very dangerous because you can't sense it. By the time symptoms appear, it may already be too late. So to combat this, they would use oxygen monitors or other alarms to go off when oxygen levels drop below 19.5%. And this is just our final summary of LOX production. Starting off with step number one, molecular sieve adsorption. So before we cool the air, we have to clean it because if there are any impurities in it, like water or carbon dioxide, they could become solids and safety hazards. Second step, Lindy-Hampson liquefaction. So the Lindy-Hampson cycle is how we get air cold enough to become a liquid. Compressed air is cooled in heat exchangers and then expanded, and then the pressure drop causes cooling, and eventually part of the air becomes liquid. And moving on to step number three, double column distillation. So this process utilizes a high pressure column and a low pressure column, and the pressure difference allows heat integration between the condenser and the boiler. Nitrogen's more volatile, so it's going to be part of our top stream, concentrates towards the top, while oxygen is more volatile, so it concentrates towards the bottom. And our final step, propulsion relevance. So LOX is the universal oxidizer in high performance rocketry. Yeah, it's just very relevant to the rocket industry. Thank you.